175 kilometers an hour and still climbing. That is the wind wrapping around the center of Typhoon Mekkhala tonight. A storm that formed from a harmless cluster of thunderstorms just days ago and has exploded into a monster aimed straight at southern Japan. It is hours from crossing the line we reserve for the very worst storms on Earth, the super typhoons, and the islands in its path are home to more than 1 million people. Yet the thing that makes this storm's target so unsettling has nothing to do with the wind at all. It is what has been silently loading beneath those islands for 250 years. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you do not miss any of our nightly debriefs, and drop a comment and tell me where you're watching from. Let's get into it. Part 1. The storm that is still growing. Right now, while you're watching this, a storm is doing the single most dangerous thing a storm can do. It is getting stronger, fast, and it is doing it close to land. Its name is Mekkhala. In the Philippines, where it has already brushed past, they are calling it Francisco. The forecasters who track these systems for a living gave it a colder, more clinical label, Typhoon 07W, the 7th named storm of the Western Pacific season. But labels do not really capture what is sitting out there on the ocean tonight. What is sitting out there is a machine, hundreds of miles across, spinning up toward the upper limit of what our planet's atmosphere can build, and it is pointed almost directly at southern Japan. Let me give you the numbers, because the numbers are the story. As of the latest official bulletin, Mekkhala is being carried by maximum sustained winds of around 175 km per hour near its center, with gusts punching up past 215 km per hour. Its central pressure, which is the truest measure of a storm's raw power, has been falling through the 945, 940, 935 hectopascal range. And falling pressure means a strengthening storm. The American Forecast Center has it pegged to peak at around 130 knots of sustained wind within the next day, and 130 knots is not just a number. It is the exact line that separates an ordinary, very dangerous typhoon from the category we reserve for the worst of them, the super typhoons. So here is the situation in one sentence. A storm is climbing towards super typhoon strength over some of the warmest ocean water on Earth, and the place it is climbing toward is a chain of islands that are home to more than 1 million people. You would think that would be the whole story. A monster storm, a populated coastline, a race against the clock. That alone would be enough to fill the next 2 hours. But it is not the whole story, and this is the part that most of the coverage you will see tonight is going to leave out entirely. The islands in this storm's path are not just any islands. They sit on top of one of the most powerful geological features on the planet, a place where 2 pieces of the Earth's outer shell grind into each other far beneath the waves. It is a fault that has been quiet for a very long time. It is also a fault that, 2.5 centuries ago, rose up without warning and wiped roughly 12,000 people off these exact islands in a single morning. That is what makes tonight different. We are watching one disaster bear down from the sky onto a place that is quietly capable of producing a second one from below. And before this is over, I want to show you both, and I want to show you exactly where the real danger lies, and where it does not, because there is a lot of noise out there right now, and not all of it is true. Let me be clear about what we know, and what we're still watching, because this is a live event, and honesty about the uncertainty is part of telling it right. We know the storm exists, we know roughly how strong it is, and we know the broad direction it is heading. What we do not yet know, with certainty, is the precise hour it makes its closest pass, the exact island that catches its worst quadrant, or whether it crosses fully into super typhoon territory before it begins to weaken. Those details will resolve over the next 2 to 3 days, and they are the difference between a severe storm and a generational one. I will give you the full picture of that uncertainty later, but I do not want you walking away thinking anyone can tell you tonight exactly where the worst of this lands. They cannot. What they can tell you is that it is coming, that it is strong, and that the window to prepare is closing fast. There is one more thing worth saying before we go any further, because it frames everything that follows. The most dangerous storms in history are almost never the ones people see coming for a week. They are the ones that strengthen at the last moment, that change their character in the final hours, that catch a coastline that thought it knew what it was facing. Mekkhala has every fingerprint of that kind of storm. It is not a slow, lumbering giant that announced itself from across the ocean. It is a fast, hungry system that built itself in days and is still building, and that single fact, the speed of it, is the thread that runs through this entire story, from the water that fueled it, to the fault it is aiming at, to the people who have only hours left to get ready. Stay with me, because to understand why this particular storm, aimed at this particular stretch of ocean, has the people who study these things paying very close attention, we have to go back to where it began, only a few days ago, as nothing more than a cluster of thunderstorms over an empty patch of sea. Part 2. Born over the warmest water on Earth. Every monster has an origin, and Mekkhala's origin is almost unremarkable. That is the unsettling part. Just a few days ago, on the 18th of June, there was nothing on the map worth a second glance. East and a little south of the island of Guam, out in the open tropical Pacific, a loose knot of thunderstorms was doing what thunderstorms do over warm water in June. They were drifting, clumping together, falling apart, reforming. There was no eye, no spiral, no name. If you had looked at the satellite image that morning, you would have scrolled right past it. But the ocean underneath that knot of storms was loaded, and within 2 days, that loose cluster had organised itself into a closed circulation, a true tropical storm with winds beginning to wrap around a centre. When it crossed into the zone of the Western Pacific that the Philippine Weather Service watches most closely, on the 20th of June, they gave it their own local name, Francisco, the way they name every storm that enters their waters. By then it was no longer a curiosity. It was a typhoon in the making, and then it did the thing forecasters dread. It began to intensify, not gradually, not over a week, but in a hard, fast climb that compressed days of strengthening into hours. To understand why that matters, you have to understand what a typhoon actually is, underneath all the drama. A typhoon, a hurricane, a tropical cyclone, these are all the same thing wearing different regional names, and at bottom each one is a heat engine. That is not a metaphor, it is the literal physics. The storm draws warm, moist air up off the surface of the ocean. As that air rises and the water vapour inside it condenses into cloud and rain, it releases an enormous amount of stored heat. The same heat the sun poured into that water over months. That released heat warms the column of air, makes it rise faster, drops the pressure underneath it, and pulls in even more warm air from the surface to replace what went up. Warm air in, heat released, pressure drops, more warm air in. Around and around. A typhoon is the atmosphere finding a way to move heat off the ocean and throw it toward the sky. And the warmer the water, the more fuel the engine has. Now here is the number that should make you sit up. The water Mekkhala has been crossing is sitting at somewhere around 29 to 31 degrees Celsius. In the temperature scale most of us grew up with, that is the mid to upper 80s Fahrenheit, bathwater warmth, stretching across hundreds of miles of open sea. And it is not just warm at the surface. The warmth runs down through a thick layer of the upper ocean, which means that even when the storm churns the sea and drags up water from below, the water it drags up is still warm. The fuel tank, in other words, is not just full, it is far larger than usual. That is the engine, and that is the fuel. Put a hungry heat engine over an enormous reservoir of warm water, with very little to get in its way, and it will do exactly what Mekkhala has done. It will grow, and it will grow fast. And the speed of that growth is not just a statistic, it is the whole reason this storm is dangerous in a way a slower one would not be. Consider what those few days actually contained. On the 18th, a nameless cluster. By the 20th, a named storm. By the 22nd, a system nearing the top tier of intensity on the planet and turning toward a populated coast. That is a transformation that, in many storms, would unfold over a week or more, compressed here into a span you could count on your fingers. Each step in that sequence shortened the time available to everyone downstream of it. The forecasters refining their models, the officials deciding whether to call evacuations, the families deciding whether to stay or go. A storm that takes its time hands those decisions out generously. A storm like Mekkhala hands them out on a stopwatch, and there is a particular menace in a storm that organises this cleanly, this quickly. A messy, disorganised system, even a large one, leaks its energy, never quite getting its act together. A storm that tightens into a compact, well-formed core, the way this one has, is a storm that has found efficiency, that is converting the ocean's heat into wind with brutal economy. The satellite images tell that story to a trained eye. the ragged blob resolving into a clean spiral, and then the first hint of an eye punching through the centre, the signature of a storm that has truly arrived. By the time you can see a clear eye on the imagery, you are no longer looking at a developing system. You're looking at a mature, dangerous machine, and Mekkhala crossed that line days ahead of its closest approach to Japan, with most of its favourable conditions still ahead of it. It is worth pausing on the name itself because even that carries a thread of the story. Mekkhala is a name drawn from regional mythology. A goddess associated with lightning and the thunderbolt, contributed to the rotating list of typhoon names that the nations of the Western Pacific share among themselves. The Philippines, meanwhile, keep their own separate list, and to them this same storm is Francisco. One storm, two names, depending on which patch of ocean it is crossing. It is a small preview of a confusion we will run into again later, in a far more consequential form, when two different agencies give this same storm two different strengths on the very same night. The Western Pacific, where Mekkhala was born, deserves a word too because it is not just another stretch of ocean. It is the most prolific producer of tropical cyclones on the planet, the part of the world that generates more of these storms, and more of the very strongest ones, than anywhere else. The reason is exactly the thing we have been circling: the water. This corner of the Pacific holds the largest reservoir of persistently warm ocean on Earth, a region sometimes called the warm pool, and it works like a perpetual engine room for typhoons. Storms that form here have more room to run and more fuel to burn than almost anywhere else, which is why the Western Pacific, and not the Atlantic, is where the records for the most intense tropical cyclones tend to be set. Mekkhala is forming in the part of the world most capable of building a monster, at the time of year when that engine room is heating toward its summer peak. Every piece of the setting is tilted toward intensity. But how fast is fast enough to scare the people whose job is to be calm? That has an actual definition, a specific threshold that turns an ordinary strengthening storm into something forecasters flag in red, and Mekkhala crossed it. Let me show you what that line is, and why crossing it so close to inhabited islands is the most dangerous thing a storm like this can do. Part 3. The word forecasters fear. There is a phrase that, if you ever hear a meteorologist use it about a storm headed toward where you live, you should pay attention to. The phrase is rapid intensification, and Mekkhala is a textbook case of it. Rapid intensification is not a vague, dramatic term. It has a hard number attached to it. A storm is said to be rapidly intensifying when its maximum sustained winds increase by at least 30 knots, that is roughly 35 miles per hour, within a single 24-hour period. Picture that. A storm that, at breakfast, is a serious but manageable threat, and by the following breakfast has gained the equivalent of an entire category of strength. That is the definition, and Mekkhala's climb fits it. Let me give you a feel for what that kind of climb looks like from the inside of the forecasting process, because it is genuinely unnerving to watch in real time. A forecaster looks at a storm in the evening and writes a forecast based on what it is and what the conditions around it suggest it will become. They go home, and by the time the next set of observations comes in, the storm has already moved beyond what the evening forecast called for, not a little, but a clear step up the scale. The satellite that showed a developing system now shows a tighter, colder, more organised one, with an eye trying to clear out at the centre. The pressure estimates have dropped. The whole thing has gone up a gear while the world slept. There is a particular feeling that comes with seeing that, the recognition that the storm is outrunning the forecast, and it is the feeling that precedes almost every tropical cyclone disaster that catches people off guard. The reason this matters so much for Mekkhala, specifically, is the geometry of where it is and where it is going. This is not a storm doing its rapid intensification far out at sea with a week of runway left, where the forecast has time to catch up and the warnings have time to be refined and acted upon. This is a storm doing its strengthening on approach, with the islands already inside the window of concern. When the intensification and the approach happen at the same time, the margin that normally lets forecasts converge and communities prepare gets compressed, and compressed margins are exactly where people get hurt. The storm is not just strong, it is strengthening at the worst possible moment in its life cycle, relative to the land in its path. Why does this one technical detail matter so much? It matters because of time, or rather, because of the lack of it. When a storm strengthens slowly and steadily over many days, the people in its path get something precious. They get warning. They get forecasts that have time to converge. They get evacuation orders that can be issued early. They get the chance to board up, to move inland, to get boats out of the water, to fill the bathtub and charge the phones and decide whether to stay or go. The slow storm is terrifying, but it is, in a strange way, fair. It announces itself. The rapidly intensifying storm does not. It cheats. It takes a population that went to sleep preparing for a strong storm and wakes them up underneath a far worse one. The forecast that looked survivable on Monday is catastrophic by Tuesday, and there is no longer enough time left to act on the difference. This is the scenario that has killed people again and again in the history of these storms, not because the warning was wrong, but because the storm outran the warning. And the cruelest version of this is exactly the version we may be watching. Rapid intensification is most dangerous when it happens close to land, in the final approach, when there is no longer any slack in the system to absorb a surprise. A storm that explodes in strength out in the open ocean, with a week to go, gives the forecast time to catch up. A storm that explodes in strength as it closes in on a coastline does not. Mekkhala is doing its strengthening as it swings toward the islands of southern Japan, not a week out, but days out. I want to be careful and honest here, because that is what we do on this channel. There are also forces working against this storm, and I will get to them, factors that may yet put a ceiling on how strong it gets before it arrives. The atmosphere is rarely simple, and Mekkhala is fighting a couple of headwinds even as it grows. We will look at those because they matter to the final outcome, but the underlying setup, the warm water, the open path, the timing of the intensification, all of it points the same direction. This is a storm built for a fast, dangerous climb at the worst possible moment, in the final stretch before it reaches people. Here is what makes rapid intensification so maddening for the people whose job is to predict it. Of all the things about a storm, its track and its strength, the strength is the harder one to forecast, and rapid intensification is the hardest part of strength. We have gotten genuinely good, over the decades, at predicting where a storm will go. The forecast cones have shrunk, the track models have improved, and a storm's path 3 days out is now something forecasters can often draw with real confidence. But predicting exactly when a storm will undergo one of these sudden bursts of strengthening, and how far it will climb before it stops, remains one of the great unsolved problems of the field. The processes that govern it happen at scales smaller than the models can fully resolve, in the fine structure of the storm's core, and they can switch on and off in ways that are still partly a mystery. What that means in practice is that rapid intensification events have a long and brutal history of being underpredicted. Again and again, storms have been forecast to reach a certain strength, and have instead blown past it, sometimes by a wide margin, in the final day before landfall. Communities that prepared for one kind of storm met another, and the cruelty of it is structural, not a failure of any individual forecaster. It is baked into the physics. The very conditions that produce rapid intensification, a warm and thick ocean, and a calm upper atmosphere, are the conditions that let a storm reach for the absolute ceiling of its potential, and that ceiling is higher than our intuitions, calibrated on ordinary storms, expect. This is why, when forecasters see that setup lining up, you hear a different tone enter their language. They stop talking in averages and start talking in worst cases, because they know the history. They know that the storms that kill the most people are so often the ones that found an extra gear at the end. With Mekkhala, that is not hypothetical. The storm has already proven it can do it, by doing it. And to really understand why it has been able to grow like this, we have to look harder at that ocean it has been feeding on, because the warmth under Mekkhala is not just a local accident of weather. It is part of something larger, something that is quietly changing the ceiling on how strong these storms can get in the first place. Let me show you what is happening to the water. Part 4. The fuel tank is getting bigger. If you want to know how strong a typhoon can become, do not look at the sky, look at the sea. For a long time, when people thought about what made a hurricane or a typhoon dangerous, they thought about the wind, the rain, the things they could see and feel. But the scientists who study these storms learned to look downward, at the temperature of the ocean, and crucially, at how far down that warmth extends. They gave it a name, ocean heat content, and it has become one of the most important numbers in the whole field. It is not just how hot the surface is, it is how much total heat is stored in the upper layer of the sea, ready to be handed up to a passing storm. Here is why the distinction matters. When a typhoon sits over the ocean and churns, its winds drag the surface water around and pull cooler water up from below. Normally, that is the storm's own break. It stirs up colder water. The colder water starves the engine of fuel and the storm weakens. It is a built-in safety valve. But when the warm layer is thick, when the heat runs far down instead of sitting in a thin skin on top, that safety valve fails. The storm churns, and the water that comes up is still warm. The brake does not engage, and the engine just keeps running. That is the situation Mekkhala has been exploiting. Not just a warm surface, but a thick loaded upper ocean with the brake disabled. It is the difference between a campfire and a furnace with the door welded open. And we can actually watch this happen, which is part of what makes the modern era of storm science so different from the past. There are satellites overhead and instruments in the ocean, drifting floats and buoys, that measure not just the surface temperature but the heat stored below, and they let forecasters see, before a storm even arrives, whether it is about to cross a stretch of unusually favourable water. When a system like Mekkhala is approaching one of these warm reservoirs, the forecasters can see the fuel waiting on the map, the way you might see a tanker truck parked in the path of a fire. It does not tell them exactly how the storm will respond, but it tells them the potential is there, and it is one of the reasons the warnings for this storm carried such urgency from early on. The fuel was visible in advance. What is harder to convey, and more important, is just how much energy we're talking about. A mature typhoon releases heat at a rate that staggers the imagination, far beyond anything human civilization produces, the equivalent, by some estimates, of many times the total electrical generating capacity of the entire planet, poured out continuously, hour after hour for days on end. That is the scale of the thing drawing its power from the warm pool right now, and every fraction of a degree of extra ocean warmth, every extra metre of warm water depth, adds to the reservoir that scale of machine can draw from. When people say the ocean is the engine of these storms, they are not being poetic. They are describing the single largest energy transfer happening anywhere on the surface of the Earth, and a warming ocean is, quite literally, putting more fuel in the tank. Now, here is where we have to widen the lens, because this is not only about one storm in one June. Across the world's tropical oceans, that stored heat has been climbing. The waters that feed these storms have been running warmer, and the warm layers have been growing thicker, and that has a direct, measurable consequence. It raises the ceiling. It lifts the maximum strength that a storm is physically capable of reaching if everything else lines up. And it does something else, something that connects directly back to what we just talked about. Warmer, deeper ocean heat makes rapid intensification more likely. The studies that have looked at this find that storms passing over unusually warm patches of ocean, sometimes called marine heat waves, are significantly more prone to those sudden, dangerous bursts of strengthening. The very behaviour that makes Mekkhala so threatening, the fast climb in the final approach, is the behaviour that a warming ocean encourages. We are, in effect, loading the dice toward exactly this kind of storm. I want to be precise about what I am and am not saying, because this is where a lot of coverage goes off the rails in one direction or the other. I am not telling you that warming oceans created Mekkhala, or that this one storm is proof of anything by itself. A single storm is weather, and weather has always produced monsters. What the science supports is something more careful and, honestly, more unsettling. It is that the background conditions, the deck these storms are dealt from, have shifted. The stronger storms are being given a higher ceiling and a faster path to reach it. Mekkhala is not an exception to the pattern. It is an example of it. Scientists actually have a way of calculating that ceiling, and it has a name, the maximum potential intensity. The idea is that for any given patch of ocean and atmosphere, there is a theoretical upper limit to how strong a storm can become, set mostly by how warm the sea surface is relative to the cold air far above it. It is the storm's speed limit, written by thermodynamics. Most storms never reach it, because something, wind shear, dry air, an unlucky track over cooler water, gets in the way first. But the limit itself rises as the ocean warms. Make the sea surface warmer, and you raise the speed limit on every storm that crosses it. The stronger storms, the ones that manage to reach for that ceiling, are the ones that show the change most clearly, because they are the ones actually testing the limit. And the ocean has been warming in a way that is no longer subtle. Beyond the general, year-over-year rise in sea temperatures, there is a phenomenon that has become far more common in recent years, the marine heat wave, a patch of ocean that runs dramatically hotter than normal for weeks or months at a time. These are not small anomalies. They are persistent reservoirs of excess heat, and when a developing storm happens to track across one, It is like a car hitting a stretch of open highway with the speed limits suddenly removed. The research connecting these warm patches to rapid intensification is some of the most important work in the field right now, and the conclusion is consistent. Storms crossing unusually warm water are markedly more likely to undergo those sudden, dangerous bursts of strengthening, and to reach higher peaks when they do. Stack it all together, a warmer baseline ocean, a thicker warm layer that disables the storm's own brakes, more frequent marine heat waves, and a rising ceiling on maximum strength, and you are not describing a freak. You are describing the deck these storms are now being dealt from, a deck quietly stacked toward exactly the behavior Mekkhala is showing, and that is the larger frame that this single storm sits inside. A specific monster, born over a specific warm pool, behaving exactly the way a warming ocean would lead you to expect. But knowing how strong a storm can get still leaves a very practical question hanging, the question everyone watching in Japan is asking tonight. Just how strong is this thing actually right now? Because depending on which forecast you read, you will get two different answers, and that confusion is not an accident. Let me untangle it. Part 5. Why nobody can agree on the category. If you went looking tonight for a simple answer to how strong Mekkhala is, you ran into a wall. One source called it a Category 4, another called it a super typhoon, a headline screamed Category 5, and you would be forgiven for thinking that somebody's exaggerating, or somebody's hiding something. Neither is true. What you ran into is one of the most genuinely confusing things about these storms, and once you understand it, you will read every tropical forecast for the rest of your life with clearer eyes. The confusion comes down to a single, almost absurd technicality. Different weather agencies measure the wind differently, not the storm differently, the wind differently. When an agency tells you a storm's maximum sustained wind, they are giving you an average, because wind is gusty and chaotic and a single instantaneous reading is meaningless. The question is, an average over how long? And here the world split into two camps a long time ago and never reconciled. The American Forecast Center, the one that issues those military-style warnings for the Pacific, averages the wind over 1 minute. Most of the rest of the world, including the Japanese agency and the Philippine agency that watch this storm most closely, average it over 10 minutes. That sounds like a trivial difference. It is not. A 10-minute average smooths out the brief, violent peaks. A 1-minute average catches more of them. So the very same storm measured at the very same moment will always look a little stronger on the 1-minute scale and a little gentler on the 10-minute scale. The rule of thumb forecasters use is that the 10-minute number runs roughly a tenth lower than the 1-minute number for the same storm, same wind, same typhoon, two different headline figures depending on who is holding the stopwatch. You can see why this matters the moment you try to compare storms across history or across ocean basins. A storm described as a 150-mile-per-hour typhoon by one agency, and a storm described as a 130-mile-per-hour typhoon by another might be the very same strength, just measured by different rulers. People who do not know about the two conventions end up comparing numbers that were never meant to be compared directly, and they reach confident conclusions that are simply wrong. This storm was stronger than that one. This basin breeds bigger storms than that one, when the entire difference is in the measurement. It is one of the quiet traps in the whole subject, and it trips up not just the public but sometimes even careful commentators who should know better. For Mekkhala, the practical upshot is simple. Do not get attached to a single number, and do not let the number you happen to see decide how seriously you take the storm. Whether a given screen tells you 4 or 5, whether it says 130 knots or 175 kilometers per hour, you are looking at a storm at or near the top of the intensity scale, aimed at a populated coastline. The label is a detail. The danger is the thing, and the danger does not change because two agencies average the wind over different lengths of time. If anything, the safest assumption, when the numbers disagree, is to plan for the higher one, because a storm sitting on the boundary between categories has already shown you it has the capacity to be on the worse side of the line. Now layer on top of that the word super typhoon. That label belongs to the American 1-minute system, and it has a precise trigger. A storm becomes a super typhoon when its 1-minute sustained winds reach 150 miles per hour, which is 130 knots. There is no equivalent official tier in the 10-minute system. The Japanese scale tops out at a category it simply calls violent. So when the American Center forecasts Mekkhala to hit 130 knots, it is forecasting a super typhoon by definition. And at the same time, the Philippine Bulletin can accurately describe that same storm as merely nearing super typhoon category, because it is reading the lower 10-minute number. Both are correct. They are just speaking two different dialects of the same language. So when you saw Category 5 on one screen and Category 4 on another, you were not watching anyone lie. You were watching the gap between two measurement conventions, played out in real time over a storm that happens to be sitting right on the boundary between them. And here is why I am spending time on this, instead of just handing you a single dramatic number and moving on. Because that gap is exactly the kind of thing that gets twisted into something it is not. Later in this briefing, I'm going to show you people online insisting that the authorities are deliberately downplaying this storm, hiding its true strength, and they will point to precisely this discrepancy as their proof. They will say, look, one source says 5 and the official one says 4. They are covering it up. And it will sound convincing if you do not know what you now know. You are not being deceived. You are watching two rulers measure the same object and disagree at the last decimal. For our purposes tonight, the honest way to describe Mekkhala is this. It is, by any measure, at least a high-end Category 4 storm, and on the American scale it is forecast to cross the super typhoon line, if it has not already by the time you hear this. The difference between those two descriptions is a few knots and a few hours. It does not change the danger. A storm at this strength, aimed at populated islands, is a catastrophe in waiting whether the label on it reads 4 or 5. There is a deeper reason this two-scale confusion is worth your time, beyond just reading tonight's headlines correctly. It is a perfect small example of how easily real information gets misread as deception. Nobody designed these two systems to confuse the public. They arose separately, in different countries, for different operational reasons decades ago, and each one is internally consistent and scientifically sound. The 1-minute average suits the agency that grew up serving aviation and the military, where the brief peak gust that can flip an aircraft matters most. The 10-minute average suits the agencies that grew up serving the general public and shipping, where the sustained push of the wind over time is what counts. Both are right. They are just answering slightly different questions. But because they produce different headline numbers for the same storm, they create a gap, and gaps are where misinformation breeds. The human mind does not like two authorities disagreeing. It wants to resolve the tension, and the easiest resolution, the one that feels savvy and skeptical, is to assume one of them is lying. Somebody must be hiding the truth, and once that suspicion takes hold, every honest discrepancy becomes evidence of a cover-up. This is worth understanding not just for this storm but for almost every confusing thing you will ever meet in a fast-moving disaster. The first explanation that occurs to people for any inconsistency is conspiracy, and the real explanation is almost always something more boring and more human. Two systems built by different people for different reasons, both doing their best, producing numbers that do not quite line up. So carry this forward. When the numbers on Mekkhala seem to disagree over the coming days, you now know why, and you know it is not a sign that anyone is lying to you. But knowing how strong the storm is only answers half the question. The other half, the half that decides who actually gets hurt, is where it goes. And the path this storm is on is being drawn by something invisible, a feature of the atmosphere that you cannot see on any satellite picture, but that is steering this monster like a hand on the small of its back. Let me show you the track and why it bends the way it does. Part 6. The Invisible Hand. Steering it. A storm this size does not choose where it goes. It is pushed. And to understand where Mekkhala is being pushed, you have to picture something you cannot see, a great dome of high pressure sitting over the Pacific to the north and east of the storm. Meteorologists call it the subtropical ridge, and you can think of it as a mountain made of air, a sprawling region where the atmosphere is sinking and heavy and settled. Storms cannot push through it, so they are forced to slide around its edge, the way a leaf in a stream is carried around the outside of a boulder. For the last few days, that ridge has been parked to Mekkhala's northeast, and so the storm has been steered along its southern flank, carried west and a little north, away from the open ocean and toward Asia. That is why the Philippines got a scare but not a direct hit. The track ran the storm past the northern Philippines, close enough to whip up dangerous monsoon rains and rough seas, but the steering current kept the core offshore, out over the water, where it could keep feeding and growing instead of tearing itself apart on the mountains of Luzon. For the people of the northern Philippines, that was a reprieve. For the storm, it was a gift, an uninterrupted runway over warm water. This is one of the cruel ironies of how these storms behave. The very thing that spared the Philippines from a direct hit, the steering current that held the core offshore, is the same thing that allowed Mekkhala to keep strengthening without interruption. A storm that ploughs into a large landmass is, in a sense, diffused by it. The land cuts the storm off from its ocean fuel, the rough terrain tears at its circulation, and it weakens rapidly, often dramatically, within hours of moving inland. A storm that stays over open water does none of that. It keeps feeding, keeps organizing, keeps building. By threading the gap between the Philippine landmass and the open Pacific, Mekkhala got the best of both worlds from its own point of view, close enough to the steering flow to be carried along, but never close enough to land to be torn apart. The result is a storm arriving at the Ryukyu with its strength intact, or still growing, rather than one already worn down by an earlier encounter with land. It is worth sitting with what that means for the islands ahead. They are not going to receive a storm that has already spent some of its fury on someone else. They are first in line for a system that has had an uninterrupted run over warm water to build itself, with nothing between it and them but more ocean. In the grim arithmetic of these events, that is close to a worst-case setup, a storm that intensified freely, steered cleanly, and arrives at its target near the peak of its power rather than on the downslope. The Ryukyus are not catching the tail end of this storm, they are catching it close to its prime, but ridges are not permanent walls, they weaken, they retreat, they develop gaps. And the forecast is for this one to relax its grip just enough, at just the right time, to let Mekkhala do what these recurving storms so often do. Instead of continuing straight into the Asian mainland, the storm is expected to feel the weakness in the ridge, turn to the north, and then begin curving back toward the northeast. That bend, that hook in the path, is called recurvature, and it is one of the most important and most difficult things forecasters try to predict, because exactly when and where a storm makes that turn decides everything about who it hits. And for Mekkhala, the turn aims it at the Ryukyu Islands of southern Japan. Let me orient you, because this geography is about to matter a great deal. The Ryukyus are a long, thin chain of islands that arc southwest from the main body of Japan down toward Taiwan, like stepping stones across the sea. At the southern end sit the Sakishima Islands, including Miyako and the Yaeyama group around Ishigaki. Further up the chain sits the main island of Okinawa, the largest and most populous of them, home to well over 1 million people and to some of the largest American military installations anywhere in the Pacific. These islands are not a remote outpost. They are a densely settled, strategically vital stretch of Japan, and they are strung out directly across the path this storm is now expected to take. The timing, as forecasters see it now, runs something like this. The southern Sakishima Islands are looking at the worst of the direct wind and waves around the 25th of June. The Okinawa main island region comes into the firing line around the 26th, and ahead of all of that, the storm's enormous moisture shield, working together with a weather front draped across Japan, is expected to start wringing out heavy rain over the southern Japanese island of Kyushu and across western Japan as early as the 23rd, days before the core itself arrives. I want to be honest about the uncertainty here, because forecasting that recurvature turn is genuinely hard, and small changes in when the storm hooks north translate into large changes in exactly which islands take the worst of it. The cone of possibility is real, but the broad shape of this is not in much doubt. A powerful storm is turning toward a populated island chain, and the clock on its arrival is measured now in days, not weeks. It is worth understanding why that turn, the recurvature, is so hard to nail down, because the difficulty is the reason the forecast keeps a cone of uncertainty around it, instead of a single confident line. The timing of the turn depends on a delicate negotiation between the storm and that ridge of high pressure steering it. As the ridge weakens, a gap opens, and the storm slips north through the gap. But exactly how fast the ridge weakens, and exactly how wide the gap becomes, and exactly how the storm responds, all of that is governed by features in the atmosphere thousands of miles away. The meandering of the high-altitude jet stream, the passage of upper-level troughs and ridges that are themselves only partly predictable days out. A small error in any of those translates into a meaningful shift in where Mekkhala makes its hook. This is why forecasters run not one model, but many, dozens of simulations of the atmosphere, each started from slightly different initial conditions, and watch where the cluster of solutions points. When the models agree tightly, confidence is high and the cone is narrow. When they spread out, the cone widens, and the honest message becomes a range of possibilities rather than a single track. For a storm threatening a chain of islands strung out across hundreds of miles of sea, that spread matters enormously, because the same storm that gives one island a glancing blow could give the next island down the chain a direct hit, depending on where in the cone the truth falls. So when you look at the forecast for Mekkhala and see a band of uncertainty rather than a confident line into a single island, understand that the band is not the forecasters hedging or being timid. It is them being honest about a genuinely hard problem. The cone is not a prediction of where the storm will not go. It is a map of where it still might. So that is the where and the when. The next question is the one that actually keeps emergency managers awake. What does a storm of this strength actually do to islands like these when it arrives? Because it is not one threat. It is three, and they arrive in a sequence, each one capable of killing on its own. Let me walk you through what the people on these islands are truly facing. Part 7. What a monster does to an island. When a storm like Mekkhala reaches a place like the Ryukyu Islands, it does not announce itself with a single blow. It arrives as a siege, and the first weapon it brings to bear is the wind. We talk about wind speed in numbers, 175 kilometers per hour, gusts past 215, but numbers go numb after a while, so let me translate. At the strength Mekkhala is carrying, the wind is no longer something you lean into. It is a physical force that rips roofing from buildings, peels signs and siding off structures, snaps power poles, and turns anything not bolted down, garden furniture, sheet metal, roof tiles, into projectiles moving fast enough to kill. On exposed islands, where the wind comes straight in off the open sea with nothing to slow it, there is no shelter from it except solid walls and the decision to be behind them well before it arrives. The power goes early and it stays out. Communication drops, and for the hours that the eye wall, the ring of fiercest wind around the calm centre, passes over an island, the safest thing anyone can do is simply not be outside, because outside is not survivable for long. But the wind, as frightening as it is often not the deadliest part. The water is. A storm this powerful shoves the sea ahead of it. The combination of the wind physically piling water against the coast and the low pressure at the storm's centre letting the ocean bulge upward produces what we call storm surge, a dome of seawater that the storm drives onto the land. On a low-lying island or a populated coastal flat, surge is the great killer. It does not knock on the door. It comes in as a wall, floating cars, collapsing the lower floors of buildings and dragging everything it touches back out to sea as it withdraws. The Sakishima Islands, sitting at the southern end of the chain and first in line, are exactly the kind of low exposed targets where surge does its worst work. And the surge does not care much whether the headline wind number read 4 or 5. It responds to the size and strength and slow approach of the whole storm, and a broad, powerful system can pile up a devastating surge even if its peak winds wobble a little in the final hours. It is worth understanding, too, that an island is in some ways the worst possible place to meet a storm like this, precisely because there is nowhere to go. On a continent you can drive inland, away from the coast, out of the surge zone, putting distance between yourself and the worst of the water. An island offers no such escape. The whole of it is coast. Every direction you run still ends at the sea, and on the smaller islands of the chain there is no interior, no safe inland refuge, only the question of which building is strong enough and which ground is high enough. That geography turns the ordinary calculus of a storm into something more claustrophobic. The people of these islands are not deciding whether to flee the storm. For the most part, they cannot. They are deciding only how and where to endure it, and the margin for error in that decision is thin, and the storm will isolate them as it arrives, which is its own distinct danger. When the wind reaches its peak, the bridges between islands close, the ferries stop, the aircraft are long since grounded, and the airports shut. For the hours of the worst of it, and often for days afterward as debris is cleared and power is restored, these communities are on their own, cut off from outside help by the same water that surrounds them. Emergency responders cannot reach a place in the middle of a typhoon. Whatever the islands have prepared before the storm, in supplies and shelter and plans, is what they will have to survive on until the system passes and the sea calms enough for help to cross it. That isolation is why the preparation has to be finished early, and why it has to assume the help will be delayed. And then there is the third weapon, the one that arrives first and lingers longest. The rain. A storm of this size carries an almost incomprehensible amount of water in the air around it, and when that moisture meets the mountainous terrain of these islands and of mainland Japan beyond, it is forced upward, cooled, and squeezed out as torrential rain. The forecasts already show the heavy rain reaching Kyushu and western Japan on the 23rd, well ahead of the storm's centre, because the storm is feeding moisture into a weather front that is sitting across the country. That means flooding and landslide danger over a region far wider than the islands the eye actually crosses, and for far longer than the day or two the core is present. Mountainous Japan is acutely vulnerable to this. Saturated slopes give way. Rivers that were placid in the morning become killers by night. People who are hundreds of miles from where the storm makes its closest approach can still find themselves in a genuine fight for their lives against water falling out of the sky. So picture the full sequence as the islands will experience it. First, days of building rain spreading far ahead of the storm, soaking the ground and swelling the rivers. Then the wind, climbing through the night until the eye wall arrives and the world outside becomes a blur of flying debris. Then, at the coasts, the surge, the sea itself coming ashore. 3 distinct disasters stacked on top of each other, delivered by one system over several days. That is what more than 1 million people in the Ryukyus, and many millions more across western Japan, are now bracing for. Let me put the wind into terms you can feel, because the numbers really do go abstract after a while. At the strength Mekkhala is carrying, the force the wind exerts on whatever it hits is not a little stronger than a regular storm. It is dramatically stronger, because the force of wind does not climb in step with its speed. It climbs with the square of its speed, and the destructive power climbs faster still. Double the wind speed, and you roughly quadruple the pressure it puts on a wall, a roof, a tree, a power line. This is why there is such a yawning gulf between a moderate storm and a top-end typhoon. It is not twice as bad, it is many times as bad. A wind that would merely rattle the windows in a weaker storm becomes, at this strength, a wind that strips the building apart and turns its pieces into weapons. That nonlinear math is the reason forecasters obsess over the difference between a Category 3 and a 4 and a 5. Each step up is a far larger jump in destruction than the numbers alone suggest. The surge deserves the same careful treatment because it is the most misunderstood killer in these storms. People hear wind speed and picture the danger, but historically in tropical cyclones around the world it is the water, not the wind, that takes the most lives. And the reason surge is so deadly is that it defeats the one instinct that keeps people alive in a storm, the instinct to shelter in place. A sturdy building will protect you from almost any wind. It will not protect you from the sea rising into and over it. Surge drowns people in their own homes, in the very places they fled to for safety, and it does it fast, with little warning, often in the dark. On the low coasts of the Sakishima Islands, where there is little high ground to retreat to, that threat is at its most acute, and it is why, if the order comes to move to higher ground or to evacuate entirely, that order is not a suggestion to be weighed against the inconvenience. It is the single most important decision anyone in the surge zone will make, and the rain, the third weapon, has a cruelty all its own, which is that it does its worst far from the storm and long after the wind has passed. A mountain does not need the eye of the typhoon to flood, it only needs the river of moisture the storm flings ahead of itself, wrung out against the high terrain. And it is a lot. It would be more than enough for any briefing, but remember what I told you at the very start. The storm is only the danger we can see. Beneath these same islands, beneath the surge zone and the harbours and the airfields, lies something that has been quiet for 2.5 centuries, and that has, in living memory of these islands, done something far worse than any storm. To understand why the geography of this particular target unsettles me, we have to stop looking at the sky and start looking at the ground. Let me take you down to the trench. Part 8. The Fault Beneath the Target. Here is something almost no one watching this storm will tell you tonight. The islands Mekkhala is aiming at are not sitting on solid, settled ground. They are sitting on the edge of one of the most powerful machines on Earth, and that machine has been loading itself in silence for a very long time. Run your eye along that chain of islands, from the main island of Japan down toward Taiwan, and just offshore on the ocean side, the seafloor plunges away into a long curving canyon thousands of meters below the surface. That canyon is the Ryukyu Trench, sometimes called the Nansei-Shoto Trench, and it marks one of the great boundaries of the planet, a place where 2 of the tectonic plates that make up the Earth's outer shell come together. On one side is the Philippine Sea Plate, on the other is the edge of the Eurasian Plate that Japan rides on, and at the trench, the Philippine Sea Plate is diving down and sliding underneath, descending into the hot interior of the Earth. We call this process subduction, and subduction zones are the birthplaces of the largest earthquakes and the most destructive tsunamis our world has ever produced. To picture what is happening down there, far below the warm surface water the storm is feeding on, imagine the slow-motion collision in cross-section. The Philippine Sea Plate, carrying the floor of that part of the ocean, moves toward the islands, and when it meets the edge of the plate Japan rides on, it bends downward and slides beneath, descending at a shallow angle into the hot interior of the planet. The boundary between them, the surface where the two plates are in contact, is the megathrust, and it is the most dangerous single feature in the whole arrangement. It is along that contact that the plates lock, that strain accumulates, and that the great earthquakes eventually break. The islands sit on the upper plate, riding above the descending slab like a passenger on the back of something enormous and slow. The motion is not fast by any human measure. These plates converge at a pace measured in centimetres per year, about the rate your fingernails grow. But multiply even a few centimetres a year by centuries of being locked and unable to slip, and you arrive at metres of stored displacement, metres of accumulated strain waiting in the rock. When a locked megathrust finally releases, it can move in seconds, the distance it was prevented from moving over all those years, lurching forward and snapping upward, and it is that sudden upward snap of the seafloor that launches a tsunami. The water above the fault is simply lifted, all of it at once, and that lifted water spreads outward as a wave. This is the machinery that sits beneath the Ryukyus, quiet, slow, and loaded, and it is the machinery that ran, catastrophically, on one morning 2.5 centuries ago. The islands themselves exist because of this collision. The Ryukyu arc, that gentle curve of land, was thrown up by the same grinding convergence that built the trench. So the people of these islands live, quite literally, on the product and the edge of a slow-motion tectonic catastrophe that has been unfolding for millions of years. Most of the time, you would never know it. The islands are green and warm and beautiful, the kind of place people fly across the world to visit. The machine underneath them works on a timescale so slow that a human lifetime cannot perceive it. But slow does not mean gentle. At a subduction zone, the two plates do not slide past each other smoothly. They catch. They lock together along their contact, and as the lower plate keeps trying to descend, the locked patch does not move. Instead, it bends. It deforms. It stores the strain, the way you can bend a wooden ruler further and further, feeling the tension build under your fingers, while the ruler stays in one piece until the instant it does not. The energy goes in slowly, over centuries. It comes out in seconds. Now, for a long time, the conventional wisdom about the Ryukyu Trench was reassuring. Compared to the monster subduction zones that everyone knows about, the one off Japan's main coast that produced the Great Quake of 2011, or the one off the Pacific Northwest of North America, the Ryukyu zone seemed quieter. The scientific phrase for it was weakly coupled, meaning the plates were thought not to be locked together very tightly, but rather to be slipping along more gradually, releasing their strain in smaller, less catastrophic increments. In the historical record of the last few centuries, there was no clear evidence of a truly great interplate earthquake here. Nothing in the magnitude 8 and above ranged from the main plate boundary, and so it was easy to file the Ryukyus under places that get storms, not places that get the very biggest earthquakes. That comfortable picture has been coming apart, and the thing that has been taking it apart is not speculation or fear, it is measurement, the slow, patient, unglamorous work of watching the ground itself, millimetre by millimetre, to see what it is actually doing. I will get to what those measurements are showing, because it genuinely changes how you should think about this place. It is worth understanding why subduction zones, specifically, are the source of the very largest earthquakes our planet produces, because it explains exactly what kind of danger is coiled beneath these islands. Earthquakes happen on many kinds of faults, but there is a ceiling on how big most of them can get, set by the size of the fault surface that can break at once. A typical crustal fault, the kind that runs through a continent, is limited in how large an area it can rupture in a single event, and so it is limited in its maximum magnitude. A subduction zone has no such limit. The contact between the diving plate and the overriding plate is a single continuous surface that can stretch for hundreds, even more than 1,000 kilometers along the boundary, and tens of kilometers down into the Earth. When a large fraction of that surface lets go at once, the result is an earthquake of a scale no other kind of fault can match. Every earthquake the planet has ever produced above magnitude 9 has come from a subduction zone. They are simply the largest engines of sudden energy release on Earth, and it is precisely because they are so large and so slow and so silent in their loading that subduction zones are the hardest hazards for human beings to take seriously. Our instincts are built for dangers that move on human timescales: the predator in the grass, the fire spreading through the trees, the flood rising in the river, a threat that announces itself only once every few centuries, that spends the entire span of a human life looking like nothing at all, slips right past the instincts we use to judge what is dangerous. We are simply not wired to fear a thing that has not moved in 250 years, even when the measurements tell us it is loading toward release. The quiet disarms us. It is the same blind spot that lets people build and live and forget along every great fault on Earth, not out of foolishness, but because the human mind cannot hold a danger vivid in its imagination for 2.5 centuries between events. The trench beneath the Ryukyus is exploiting that blind spot right now, the same way it was in 1771, when the people who felt that modest tremor simply went back to what they were doing. And the way they store that energy is the part that makes them so treacherous to live above. Because the plates are locked, because the strain accumulates slowly and silently over centuries, a subduction zone gives almost no day-to-day sign of what it is doing. There is no rumbling, no visible movement, no obvious warning that the rock is being bent toward its breaking point. The land above may rise or tilt by amounts too small to feel, detectable only by precise instruments. To anyone living on the surface, the years between great earthquakes look like peace. They are not peace. They are the loading phase, the slow draw of the bowstring, and the longer it goes on quietly, the more energy is being stored for the eventual release. This is the uncomfortable truth about every subduction coastline on Earth, and it applies with full force to the Ryukyus. The quiet is not evidence of safety. In a strange way, the quiet is the warning, because a locked fault that has not released in a very long time is, by definition, a fault that has been accumulating strain for a very long time. But first I want to take you back to a specific morning, on these specific islands, because the Ryukyu Trench is not a hypothetical danger. It has already shown, once in a way that was written down and remembered, exactly what it is capable of, and the islands it did it to are the very same Sakishima Islands, now sitting first in line for this storm. To understand the warning, you have to understand what happened here in the year 1771. Part 9. The morning the sea stood up. On the morning of the 24th of April, in the year 1771, the people of the Yaeyama and Miyako Islands, at the southern end of the Ryukyu chain, felt the ground shake. By the standards of this region, the shaking was not even especially violent. Many who felt it would have assumed it was just another tremor, the kind these islands get and shrug off. They were wrong, and their mistake is one of the most important lessons in the entire history of natural disasters. Because out at the trench, the fault had finally let go. And the kind of earthquake it produced is one of the most treacherous of all, the kind scientists sometimes call a tsunami earthquake. These are events that release their energy slowly and quietly, in a way that produces surprisingly weak shaking on land for their true size, while still violently shoving the seafloor upward. The shaking lies to you. It tells you it was a minor event. And while you are believing that lie, the ocean is already moving. What came ashore on those islands is almost beyond belief. The earthquake had displaced a wall of seawater, and that wall rose up as it reached the shallows and crashed onto the southern coasts of the Sakishima Islands. The local run-up, the height the water reached as it surged inland and up the slopes, was recorded in historical accounts at extraordinary figures in places many tens of meters above the normal sea level. Entire villages that had stood for generations were swept away completely. The water reached places no living person had ever seen the sea touch. To grasp how a wall of water can climb so improbably high, you have to understand what happens when a tsunami meets the land. Out in the open ocean, a tsunami is almost nothing to look at. A long, low swell that a ship might not even notice as it passes underneath. But it carries its energy through the entire column of water, from surface to sea floor, and it moves at the speed of a jetliner. As it reaches the shallows near a coast, the front of the wave slows while the water behind it keeps rushing in, and all that energy, all that water, piles up and rears upward. The shape of the coastline can focus it further funneling the wave into a bay or up a slope, concentrating its height in particular spots. This is how a tsunami that was a gentle swell at sea becomes, at certain points on certain coasts, a wall of water reaching heights that seem impossible, carrying boulders the size of houses inland, a few of which still rest on these islands today as markers of how far the water came. That detail, the boulders, is part of how scientists reconstructed the event long after the fact, reading the evidence the wave left behind, the displaced coral blocks, the deposits of sand carried far inland, the gaps in the historical record where communities simply ceased. It is painstaking work, piecing together a disaster from before the age of instruments, and it is the same kind of work that established the recurrence interval, the rhythm of several hundred years between these great waves. The 1771 event is the most recent verse of that long, slow song, and the islands now bracing for a storm are sitting exactly where the next verse, whenever it comes, will be sung. The death toll from that single morning is estimated at roughly 12,000 people. It is worth pausing on what a number like that meant for a place like this. These were not large, dense cities with reserves of population to absorb a loss. They were island communities, and 12,000 dead represented a catastrophic share of everyone who lived in the affected districts. In some places, the majority of a village gone in a single morning. The survivors faced a shattered world, fields ruined by salt water, fishing fleets destroyed, the basic machinery of survival swept away along with the people. And the suffering did not end when the water withdrew. In the years that followed, the broken communities were hit by famine and disease, the slow secondary killers that follow any disaster that wrecks the systems people depend on to feed and care for themselves. The full toll of the 1771 event, counted honestly, reaches well beyond the people the wave took directly, into the long, grinding aftermath that the wave set in motion. This is the part of a disaster that rarely makes the dramatic retelling, the long tail of it, the decades of recovery, the demographic hole that takes generations to fill. It is also the part that matters most for understanding why these events are remembered with such weight in the places that endured them. A storm passes in a day, a great tsunami passes in minutes, but the wound each leaves can shape a community for a century, and the memory of it passed down becomes part of how a place understands the ground and the sea it lives between. The Sakishima Islands carry that memory, and it is a memory of exactly the kind of event the trench beneath them is still capable of producing. 12,000. On a small island population, that was not just a disaster. It was a demographic wound that took the Yaeyama Islands the better part of a century to even begin to recover from, compounded in the years that followed by famine and disease in the shattered communities the water left behind. The event has a name in the regional memory, the Meiwa tsunami, after the Japanese era in which it fell, and the leading scientific reconstruction of it points to a shallow earthquake out on that subduction boundary, with a magnitude in the range of 8 as the source of the wave. I want you to hold those two facts next to each other, because this is the whole point. The islands that a magnitude 8 earthquake and its tsunami devastated in 1771 are the same islands, the Sakishima group, that the forecasters now have first in line for Mekkhala's wind and surge around the 25th of June. The same low, exposed southern coasts, the same stretch of sea. One disaster came from the sky, and one came from below, separated by 2.5 centuries, aimed at the same patch of ground. And the question that hangs over all of this, the question that turns a piece of history into a live concern, is simple and uncomfortable. How often does the trench do this? Because if events like 1771 happen on a rhythm, then the only thing that matters is where we are in that rhythm now. The research on the southern Ryukyu zone suggests these large tsunamis recur on a timescale of several hundred years, and it has now been more than 250 years since the last one. There is a detail about the 1771 disaster that I do not want to pass over, because it is the single most important lesson the event teaches, and it is a lesson that still saves or costs lives today. The shaking was mild for the size of the wave. This is the signature of what scientists later came to call a tsunami earthquake, an event that ruptures slowly and quietly, radiating relatively little of the sharp, violent shaking that people instinctively use to gauge danger, while still displacing an enormous volume of water. The result is a deadly mismatch between what the land tells you and what the sea is about to do. People feel a modest tremor, conclude it was nothing serious, and stay exactly where they are. And then the ocean arrives. This is why, on any subduction coast, the modern guidance is so insistent on one point. Do not wait to judge the danger by how hard the ground shook. If you're near the coast and you feel a long rolling earthquake, especially one that goes on for an unusually long time, the correct response is to move to high ground immediately, without waiting for an official warning, because the warning may not outrun the wave, and the shaking itself may badly understate what is coming. The people of the Sakishima Islands in 1771 had no way to know this. The science that explains it did not exist. They judged the danger the only way they could, by what they felt, and what they felt lied to them. We have no such excuse. The lesson is written into their islands in the most permanent ink there is, the memory of 12,000 dead. And the question the trench poses now is whether anyone is still reading it. That does not mean another is due tomorrow, or next year, or in our lifetimes. Geology does not run on a clock that precise, and I am not here to tell you the ground is about to open up. But it does mean that the old label, the comfortable one, weakly coupled, quiet, nothing to worry about, was always hiding a more complicated truth. And modern instruments have now pulled that truth into the open. Let me show you what the ground itself has been quietly confessing. Part 10. What the ground is quietly confessing. If you want to know whether a locked fault is storing up danger, you cannot just wait for the earthquake. By then it is too late. So scientists found another way to listen. They learned to watch the land itself move. Across Japan, and across many of the world's danger zones, there is a network of receivers locked onto the same satellite positioning signals your phone uses to find itself on a map. Except these instruments are bolted to the bedrock and tuned to a precision your phone could never dream of. They can detect the ground shifting by millimeters over months and years, and what they are watching for is the telltale fingerprint of a locked fault, the slow, steady deformation of the land as it gets dragged and bent by the plate grinding down beneath it. If the fault below were truly slipping freely, the land above would sit still. If the land above is being warped, it means the fault below is stuck and strain is piling up. The precision of this is worth pausing on, because it is genuinely one of the quiet marvels of modern science. We're talking about detecting the movement of solid ground by millimeters, distinguishing the slow, steady creep of a continent from the subtle bending imposed by a fault locked far below, and doing it across years of patient observation. A single measurement tells you almost nothing. It is only when you stack up the readings, month after month, year after year, and watch the land trace out a consistent pattern of deformation, that the shape of the hidden fault beneath begins to emerge. It is a little like watching the surface of a trampoline to work out the weight and position of something pressing up from underneath. You never see the thing directly. You infer it precisely from how the surface above it is bent. And what makes the Ryukyu findings carry weight is that they did not come from anyone looking to frighten people. They came from the ordinary, careful accumulation of data by scientists whose job is simply to measure the ground as accurately as possible and report what it shows. When that measurement revealed a locked patch where the comfortable old story said there should be free, harmless slipping, it was not a prediction of doom. It was a correction to the record, a quiet note that the place was more loaded than we had assumed. That is how science actually updates, not with sirens, but with a careful measurement that does not match the expectation, repeated until it cannot be ignored. The yellow light under these islands was not switched on by alarmists, it was switched on by the data. When researchers turned this technique on the southern Ryukyu Trench, they did not find the reassuring picture the old label promised. They found signs of a locked patch, a region along the plate boundary that appears to be stuck, accumulating strain, building toward release. In a study published in 2021, scientists analysing this satellite positioning data concluded that there is a meaningful slip deficit along the southern Ryukyu Trench, meaning the fault has been quietly falling behind on the motion it owes, storing that unreleased movement as strain in the rock. And if that locked region keeps loading at the rate it has been since the last great event, it is capable of producing a megathrust earthquake with a moment magnitude greater than 7.5. Other analyses of that shallow locked zone push the potential higher still, into a range from magnitude 7.5 all the way to 8.7. Sit with that upper number for a moment. A magnitude 8.7 earthquake is not a regional event. It is one of the largest classes of earthquake the planet can generate, the kind that rewrites coastlines and sends tsunamis across an entire ocean basin. And the research is saying that the shallow part of this supposedly quiet trench may be geometrically and energetically capable of one. There is more, and it deepens the unease in a precise physical way. Studies of this plate boundary have found a population of strange small earthquakes occurring at depths of roughly 15 to 18 kilometers along the fault interface, a band of what are called low-frequency earthquakes. Their importance is in where they sit. They appear to bridge the gap between the shallow part of the fault near the trench, the part that makes tsunamis, and the deeper part further down where the plates slide more gradually. In other words, they trace out the architecture of a fault that is doing complicated, active things along its whole length, not the architecture of a dead, harmless boundary. Now, I have to be scrupulously fair here, because the science genuinely is not settled, and anyone who tells you it is, in either direction, is selling something. The Ryukyu zone has, in fact, lacked clear evidence of those magnitude 8+ interplate earthquakes in the historical record, and the overall coupling really does appear weaker than at the most notorious subduction zones. The honest scientific position, laid out in the research, is a question rather than a prophecy. It asks whether a weakly coupled zone like this one could still rupture in a great tsunami-generating earthquake. And the uncomfortable answer the researchers keep arriving at is, yes, even a weakly coupled subduction zone can do this. The 1771 tsunami is the proof, written into the islands themselves. A zone does not have to be Loctite everywhere to drown its coast. It only has to let go once, in the wrong place. There is one more piece of the puzzle the instruments have uncovered, and it deepens the picture in a way that is genuinely remarkable. Along many subduction zones, including in this region, scientists have discovered that the faults do not only do two things, lock silently, and then rupture catastrophically. They do a third thing, something nobody knew about until the satellite measurements got precise enough to catch it. They sometimes slip slowly, releasing strain over days or weeks in a motion far too gentle and too gradual to be felt as an earthquake at all, a phenomenon called slow slip. These silent earthquakes, as they are sometimes called, were invisible to us until very recently. We simply did not have the eyes to see them. Now we do, and what they reveal is a fault system that is alive and active in ways the old picture never captured, constantly adjusting, locking here, slipping there, redistributing strain along its length. Why does that matter for the danger? It matters because slow slip events change the loading on the locked patches around them. When a fault slips silently in one place, it can transfer stress onto the still locked regions next door, nudging them incrementally closer to their own release. The interplay between the silent slip and the locked zones is one of the most active frontiers in earthquake science precisely because it bears on the question everyone wants answered, which is whether these silent events are harmless pressure valves or quiet triggers that load the gun. The honest answer, today, is that we do not fully know, but the very existence of this hidden activity, picked up only because the instruments finally got good enough, is another piece of evidence against the old, comfortable idea that the Ryukyu Trench is simply asleep. It is not asleep. It is doing complicated, continuous, partly understood things, and some of those things are loading the shallow, tsunami-capable part of the fault that drowned these islands before. So this is the ground that Mekkhala is bearing down on. Not solid, settled, safe ground, but a strained, loaded, quietly active fault with a documented history of catastrophe and a modern set of instruments flashing yellow. And it is precisely this combination, the storm above and the fault below, that has set off a wave of a very different kind tonight, a wave of claims and theories racing across the internet, some of them tempting, most of them wrong. We owe it to ourselves to look at them honestly and to sort the genuine danger from the noise. Let me show you what people are saying and what the science actually supports. Part 11. The theory that sounds right and isn't. Whenever a powerful storm lines up with a dangerous fault, the internet does something predictable. It connects them, and the theory writes itself so neatly that it feels true. A monstrous typhoon, hundreds of miles wide with the lowest air pressure for hundreds of miles around, is about to park itself directly over a strained subduction zone. Surely the thinking goes, all that weight, all that low pressure pulling up on the crust, all that energy, could be the nudge that finally sets the locked fault loose. Storm triggers earthquake. It is dramatic, it is intuitive, and right now it is spreading. I understand the appeal, and I want to treat it with respect, because the underlying instinct is not entirely crazy. Scientists have genuinely studied whether changes at the surface can influence faults below. There is real research into whether heavy rain, or changing water loads, or the pressure swings of large storms can nudge shallow, sensitive faults and into the curious phenomenon of slow, silent slip events that sometimes seem to respond to surface conditions. So the question itself is legitimate. It deserves a real answer rather than a dismissive wave. But here is the real answer, and it comes down to a brutal comparison of scale. The forces locked into a subduction megathrust are almost unimaginably large, the accumulated strain of centuries of plate motion, stored across a fault surface that can be hundreds of kilometers long and tens of kilometers down. The pressure changes and the loading that even the most violent typhoon imparts to the crust are, by comparison, a feather laid on the back of a freight train. The atmospheric pressure at the center of a powerful typhoon drops by perhaps 10%. That sounds like a lot, but spread over the crust and stacked against the tectonic stresses involved, it is a vanishingly small perturbation, and the historical test is the most damning evidence of all. Powerful typhoons have passed over the world's subduction zones thousands upon thousands of times throughout recorded history. If overhead storms reliably triggered great earthquakes, the pattern would be impossible to miss. The two would march together in the record. They do not. No great subduction earthquake has ever been reliably pinned on a passing typhoon. The overlap is real, the cause is not, and notice what the honest version costs you and what it gives you in return. It costs you the satisfaction of a single dramatic story in which the storm and the fault are locked in some confrontation over these islands. That story is more cinematic than the truth, and a part of all of us wishes it were real, because it would make the universe feel less random and more authored. The honest version gives you something less thrilling but far more useful, which is an accurate map of where the danger actually is. The storm is dangerous fully on its own terms, and it is coming in days. The fault is dangerous fully on its own terms, on a timescale no one can pin down. Neither needs the other to be worth your fear, and pretending they are connected does not add to the danger, it only blurs your picture of it. This is, in the end, what we are actually here to do. Not to manufacture connections that make the world feel more sinister, but to find the real ones, the ones the data supports, and to be just as clear about the connections that are not there. The genuine link between this storm and this fault is not a trigger. It is a lesson, the same lesson taught twice, about places that look safe and are not, about strain that builds in silence, about the gap between appearance and capability. That link is real, and we will come back to it. The trigger is not, and we leave it here, where it belongs, among the stories that feel true and are not. So when you hear someone insist tonight that this storm is going to wake the fault, you can hold two things in your mind at once, which is the whole discipline of thinking clearly about this stuff. You can take the danger of the fault completely seriously because it is real, and you can reject the specific claim that the storm will pull its trigger because the physics does not support it. Both at the same time, that is not fence-sitting. That is just refusing to let a real fear get hijacked by a false mechanism. And while we are clearing the air, there is a second theory that always shows up alongside the first, and it deserves the same firm, fair treatment. Someone, somewhere, is right now insisting that a storm this perfectly aimed cannot be natural, that it was steered, engineered, manufactured and pointed at Japan on purpose. The trouble with that idea is everything we spent the earlier part of this briefing establishing. We watched exactly where Mekkhala came from, an ordinary cluster of thunderstorms over warm water. We watched what is steering it, an ordinary dome of high pressure that any meteorologist could have pointed to days ago. We watched what is feeding it, an ordinary, if unusually warm reservoir of ocean heat. There is no hidden hand here. There is only physics we understand well enough to have forecast this storm's birth, its strengthening, and its turn toward Japan in advance. No technology on Earth can manufacture and aim a heat engine the size of a country. The amount of energy these storms release every second dwarfs anything human beings can produce. I want to dwell for one more moment on why these theories are so seductive, because understanding the pull of them is the best defense against being pulled. The human mind is a pattern-finding machine, and it is especially good at finding patterns in coincidence and at reaching for intention behind events. When two dangerous things line up in the same place at the same time, a powerful storm and a deadly fault, every instinct we have screams that there must be a connection, that one must be reaching for the other, that someone or something must be behind it. Random, unrelated danger is, in a strange way, harder for us to accept than a sinister plan, because a plan at least has a logic we can grasp, an enemy we can name, a story with a villain in it. Pure coincidence, the storm and the fault simply happening to share an address, feels unsatisfying, even though it is the truth. But the discipline of thinking clearly is exactly the discipline of sitting with that unsatisfying truth instead of fleeing into a tidier story. The storm is real. The fault is real. They are in the same place, and they have nothing to do with each other beyond geography. Holding all of that at once, without inventing a connection to soothe the discomfort, is harder than it sounds, and it is the whole game. Because the moment you let a false connection take over, you stop preparing for the real dangers and start bracing against an imaginary one. The person who believes the storm will trigger the quake wastes their attention on a thing that will not happen and may neglect the storm itself, which absolutely will. The false story does not just mislead, it actively pulls your guard away from where the real blow is coming from. The truth, in both cases, is less satisfying than the conspiracy and far more important. The danger is not hidden, and it is not manufactured. It is sitting in plain sight, in the warm water and the strained fault and the simple, terrible geometry of a storm and an island chain in the same place at the same time. And that brings us back to the only questions that actually matter now. What happens over the next 72 hours? What should the people in this storm's path be watching for? And what will tell us whether the worst case is unfolding or being averted? Let me walk you through what comes next. Part 12. The next 72 hours. Forecasting a storm like this is not a single prediction. It is a running argument between forces that are pushing the storm to grow and forces that are trying to tear it down, and the next 3 days are when that argument gets settled over the heads of more than 1 million people. So let me lay out, as honestly as I can, the things that will decide how bad this gets, and the specific signs that will tell us which way it is breaking. The first thing to watch is whether Mekkhala finishes its climb across the super typhoon line, and then what happens to it after that. Right now, the forecast peak sits at around 130 knots, which is, as we established, the exact super typhoon threshold on the American scale. But intensity at this level is rarely a smooth curve. The strongest storms tend to go through something called an eye wall replacement cycle, and it is one of the most important and least understood behaviors of an intense typhoon. Here is what happens. As the storm matures, the tight inner ring of thunderstorms that surrounds the eye wall, where the fiercest winds live, begins to be choked off by a second, larger ring forming further out. The outer ring slowly strangles the inner one, the inner eye wall collapses, and for a time the storm's peak winds actually fall, because the engine is rebuilding its core. To a casual observer it looks like the storm is weakening, and the headline wind number does drop. But here is the trap in that, and it matters enormously for the islands. When the storm completes the cycle, and the new, larger eye wall takes over, the peak winds may come back, but the field of strong winds has grown wider. The storm becomes broader, its reach extends further from the centre, and that has a direct consequence for the most dangerous threat of all. A wider wind field pushes a larger, more destructive dome of storm surge, and it spreads the damaging winds across a bigger swathe of coastline. So a storm that is, on paper, slightly weaker by peak wind after an eye wall replacement, can actually be more dangerous to a string of islands, because it is hitting more of them, harder, with more water. Do not let a dip in the category number fool you, and do not let anyone tell you the threat is over because the peak wind eased for a few hours. Watch the size of the storm, not just the number on it. There is a historical reason forecasters are so insistent on this particular point, the danger of the broadening storm. Some of the most destructive tropical cyclones in history were not the ones with the highest peak wind readings. They were the large, sprawling systems whose enormous wind fields drove walls of water across huge stretches of coast, drowning far more people than a smaller, more intense storm would have. Size is its own kind of power, sometimes a deadlier kind than peak intensity, because it governs how much water the storm can pile up and how much coastline it can attack at once. A storm that is, on paper, a notch below its peak, but that has swelled in size, can be carrying a larger total threat than it did at its most intense. This is exactly why a falling category number, late in the game, is not permission to relax. So as Mekkhala approaches, the question to keep asking is not simply how strong is it, but how big is it, and is it growing? A compact, ferocious storm threatens a narrow path with extreme winds. A large storm, even a slightly weaker one, threatens a wide region with surge and rain, and a longer duration of punishment. The Ryukyu Islands, strung out across the sea, are vulnerable to both kinds. but it is the broad, water-heavy version that would put the most of that island chain in danger at once. Watching the size, and not just the headline number, is how you read the true threat in the days ahead. The second thing to watch is the recurvature, that turn to the north and northeast we talked about. The single biggest source of uncertainty in this whole forecast is exactly when and where Mekkhala makes that hook, because it decides which islands sit under the worst quadrant of the storm. In any northern hemisphere typhoon, the winds and the surge are not distributed evenly. The right side of the storm, relative to its direction of travel, is the dangerous side, where the storm's own forward motion adds to its rotating winds and where the surge gets piled highest. A shift of even 100 kilometers in where the turn happens can be the difference between an island catching the ferocious right side and an island getting the merely terrible left side. This is why the forecasters keep talking in cones and probabilities, rather than single lines, and it is why the people in the Sakishima Islands and on Okinawa need to be watching the official updates hour by hour rather than locking in on a track they saw yesterday. The third thing to watch is what finally slows this storm down, because something will. As Mekkhala curves toward Japan, it runs out of the perfect conditions that built it. The ocean north of the tropics is cooler, and we already know what cooler water does to a heat engine. It starves it. The storm will also encounter stronger high-level winds, what meteorologists call wind shear, which tears at the structure of a typhoon, tilting and ventilating its core and disrupting the neat vertical chimney it needs to stay strong. We are already seeing hints of this fight. Even now, as the storm intensifies, forecasters have noted some northerly shear nibbling at its outflow on the northern side, and some drier air trying to work its way into the circulation, both of which can put a temporary cap on the strengthening. Those same forces will grow stronger as the storm moves toward Japan, and they are the reason the forecast shows Mekkhala gradually weakening from its peak. As it approaches the Ryukyus and beyond, the wind numbers stepping down from 130 knots toward 110, then 95, then lower in the days after. But, and I cannot stress this enough, weakening from a super typhoon is not the same as becoming safe. History is unfortunately full of storms that killed after they had technically weakened, and the pattern in them is almost always the same: a population that heard the word downgrade and let its guard down at exactly the wrong moment. A storm that drops a category in its final approach generates headlines that sound like relief, and relief is the most dangerous emotion a community in the path of a major storm can feel. Because the downgrade is almost never as large as it sounds, and it rarely touches the threats that actually do the killing. The surge does not care that the peak wind eased. The rivers do not care. The saturated hillsides do not care. Those threats are governed by the size of the storm, the amount of water it carries, and how slowly it moves, and a weakening storm can hold or even increase all of those even as its headline wind number ticks down. The downgrade is real, but it is a downgrade in one specific measurement, not a reprieve from the storm as a whole. The other trap in a late weakening is timing. By the point a storm begins to ease as it nears land, the window for preparation is usually already closing or closed. A family that decided to stay because they heard the storm was weakening may find that, by the time they realize the threats to them have not eased at all, it is too late to leave, the roads flooded, the bridges shut, the window gone. The decision to take a storm seriously has to be made early, on the basis of what the storm is capable of, not revised downward at the last minute on the basis of a single encouraging number. This is why the forecasters and the emergency officials fight so hard against the language of downgrades, and why they keep repeating, in the face of a weakening storm, that the danger remains. They are fighting human nature, the powerful pull toward any excuse to relax, and they are fighting the clock. A storm that drops from 130 knots to 95 knots as it reaches the islands is still an immensely powerful and deadly system, a strong typhoon by any definition, fully capable of the wind, surge, and flooding catastrophe we walked through. The weakening matters at the margins. It may be the difference between historic devastation and merely severe damage, and that is a difference worth a great deal to the people underneath it. But nobody on those islands should hear the word weakening and relax. The right response to this forecast is not relief. It is preparation, completed early, before the rapid part of this storm's behaviour steals the time to finish it. Let me give you a few concrete signposts to watch over these days, the things that will tell you, in real time, which way this is breaking. Watch the central pressure, not just the wind. Pressure is the cleaner, steadier measure of a storm's core strength, and if you see it continuing to fall, Into the low 900s or below, the storm is still deepening regardless of what the wind estimate does in any given hour. Watch the appearance of the eye on satellite. A clear, round, symmetric eye is the sign of a healthy, powerful storm with an organised core. A ragged eye, or an eye that clouds over, can be the first hint that the structure is being disrupted by sheer or dry air, the early sign of weakening, or of an eye wall replacement in progress. And watch the forward speed and the angle of approach, because a storm that slows as it nears the islands will prolong the battering and pile up more rain, while the angle of its track decides which islands sit in the dangerous right side. Watch, above all, the official forecast track updates, and watch how the cone narrows. In the early going, the band of possibility is wide, and the honest message is a range. As the storm closes in and the recurvature locks in, the models will converge, the cone will tighten, and the picture of who takes the worst of it will come into focus. The single most useful thing anyone in the path can do is to keep checking those updates, because the storm we are describing tonight may not be precisely the storm that arrives. It could be stronger, it could be weaker, it could be aimed 100 kilometers left or right of where it looks aimed now. The only way to stay ahead of a fast-changing storm is to keep looking at the freshest information and to keep adjusting. But here is the thing about all of this watching. Watching is for us, the observers at a safe distance trying to understand. For the people actually in the path, the time for watching ends well before the storm arrives, and the time for acting has to end before that, and that is the thread that runs through everything about the next 72 hours. This is a storm defined by speed, the speed at which it grew, and the speed at which the situation can change. The people who come through it best will be the ones who treat the forecast not as a promise but as a warning, and who act on the worst end of the range while there is still time to act at all. So what does acting actually look like? For the more than 1 million people now in this storm's path, and for the others watching from further away, wondering what any of this has to do with them. Let me bring it down to the ground, to the islands, and the people on them. Part 13. The million people in the path. It is easy, when you spend an hour talking about plate boundaries and wind scales and eye wall replacement cycles, to lose sight of the only thing that actually matters in all of this. There are people there. Real people going about ordinary lives who are about to have one of the most dangerous nights of those lives and who did nothing to deserve it except to live where they live. That phrase, where they live, deserves a second look, because there is often an unspoken judgment hiding inside the way people talk about disasters in faraway places. Why do they live somewhere so dangerous, the thinking goes, as if the people in harm's way had carelessly chosen a uniquely reckless place to build their lives. But step back, and the judgment falls apart. These islands have been home to people for many centuries, long before anyone could measure a fault or forecast a storm. They are home because they are home, because generations were born and raised and buried there, because they are beautiful and productive and woven through with the entire history of the people who belong to them. Nobody chose them as a gamble against catastrophe. They chose them the way people everywhere choose where they are from, which is to say they mostly did not choose at all. They inherited it. And the truth is that almost everywhere people live carries some version of this exposure, some hazard built into the ground or the sky or the sea, the coast that floods, the plain the tornado crosses, the valley below the volcano, the fault beneath the city. There is no perfectly safe place, only places whose dangers are more or less visible, more or less frequent, more or less acknowledged. The people of the Ryukyus are not unusually foolish for living where they live. They are unusually exposed right now, on this particular night, to a hazard that is bearing down on a schedule. The rest of us are exposed to our own hazards on schedules we cannot see. That is worth remembering before anyone watching from a safer seat allows themselves the comfort of thinking this could only ever happen to someone else, somewhere else. Let me put some human scale on the geography. The Okinawa main island alone is home to well over 1 million residents. Add the smaller islands of the chain, the Sakishima group to the south, the scattered communities up and down the arc, and you have a densely populated stretch of Japan that is about to be raked by a near-super typhoon. These are not empty rocks. They are cities and towns and villages, schools and hospitals and harbours, families who will spend the next days deciding whether their home is strong enough to shelter in, or whether they need to move, businesses boarding up, shelves emptying of water and batteries and rice, the whole anxious choreography that a coastal population performs when the sea is about to come for them. There is also a dimension to these particular islands that gives this storm a reach far beyond Japan. Okinawa hosts some of the largest American military installations anywhere in the Pacific, including Kadena Air Base, one of the most important air bases the United States operates in the entire region. Tens of thousands of American service members and their families live on these islands alongside the Japanese population. When a storm of this magnitude bears down on Okinawa, it is not only a Japanese emergency. It is a moment when one of the most strategically vital pieces of real estate in the Pacific has to batten down, ground its aircraft, secure its ships, and ride out the same wind and water as everyone else. The storm does not check anyone's passport. It treats the airman and the fisherman exactly alike. It is worth holding on to that image, the storm's complete indifference, because it cuts against a habit we all have of imagining that disasters somehow discriminate, that preparation or status or simply being modern and developed buys a kind of immunity. It does not. A typhoon is a physical process, the movement of heat and air and water, and it acts on whatever is in its path according to the unforgiving rules of physics, not according to who anyone is or how ready they thought they were. The wealthy island and the poor island both lose power when the lines come down. The reinforced building and the old one both face the same wind, and the difference between them is decided in advance, in the engineering, not in the moment. This is humbling, and it should be. It is a reminder that against a force on this scale, our only real power is the power we exercise before it arrives, in how we build, how we plan, and how seriously we take the warning. And the warning this time has been generous by the standards of these storms. For all that Mekkhala intensified quickly, it did not appear from nowhere. It was tracked from its birth east of Guam, named, watched, and forecast toward Japan days in advance. The people in its path have had something the people of 1771 did not have: real warning, real time, real science telling them what is coming and roughly when. Whether that warning translates into lives saved depends on the thing it always depends on, whether people believe it and act on it while there is still time. The forecast is a gift. It is only worth something if it is used. So what does the right response look like for the people there? It looks like taking the worst end of the forecast seriously right now, and finishing every preparation before the wind arrives, because once the eye wall is overhead there is nothing left to do but endure it. It means securing or bringing inside anything the wind could turn into a missile. It means having water, food, light, and a way to get information for several days, because the power will fail and it will not come back quickly. It means, for those on the low, exposed coasts where the surge does its killing, understanding that wind is survivable indoors but a wall of seawater is not, and that if the authorities say move, the time to argue has passed. And it means watching the official channels, the Japanese Meteorological Agency, the local authorities, hour by hour, rather than trusting a track or a category they saw a day ago, because we have spent this whole briefing establishing that this is a storm whose defining trait is how fast it changes. I also want to speak for a moment to the people watching this who are nowhere near Japan, who are listening from a quiet house on the other side of the world and wondering why this should matter to them. It matters for two reasons. The first is simply human. More than 1 million people are in danger tonight, and paying attention is a small act of solidarity with them, a refusal to let a catastrophe happen to strangers as if it were only weather on a map. But the second reason is colder and more self-interested, and it is the reason this channel exists. What is happening to these islands is not a freak, a one-off, a faraway problem with no bearing on anywhere else. It is a preview. The ingredients that built this storm, the warmer and thicker ocean heat, the rising odds of rapid intensification, the simple fact of more people and more infrastructure crowded onto vulnerable coasts, those ingredients are not unique to the Western Pacific. They are spreading. The coastlines that have historically felt safe from the very worst of these storms are watching their own odds quietly change, the way the Ryukyu Trench's reputation for safety quietly changed once someone actually measured the ground. There is something worth saying about Japan specifically, because if there is any nation on Earth built to meet a storm like this, it is this one. Japan has spent generations, and an enormous share of its national attention and resources, learning to live with natural hazards that would overwhelm most other places. Its building codes are among the most demanding anywhere. Its warning systems are fast and sophisticated. Its people are, on the whole, drilled and prepared and culturally fluent in the language of disaster, in a way that genuinely saves lives when the moment comes. When the storm reaches the Ryukyus and then the main islands, it will be met by one of the most disaster-ready societies that has ever existed, and that matters. It is often the difference between a storm that kills thousands and the same storm that kills far fewer, because the buildings held, the warnings landed, and the people knew what to do. But preparedness is not invincibility, and the danger in a society that prepares well is a subtler one, the danger of a storm or an earthquake that exceeds even what the preparations assumed. The seawalls are built to a height, the codes are written to a standard, the plans assume a certain worst case, and the unsettling lesson of the changing ocean and of the undermeasured fault is precisely that the worst case is not fixed. It can grow. A storm can find a strength the old assumptions did not plan for. A fault can release more than the textbook said it could. The places that prepare best are still only as safe as the accuracy of their worst-case imagination, and the whole thread of tonight has been about how that worst case has been quietly shifting, in the ocean and under the ground, while the assumptions stayed where they were. So even for a nation as ready as Japan, the right posture tonight is humility before a storm that may not read the script. That is the link between the storm above and the fault below that I promised you at the very beginning, and it is not the crude one the conspiracy theories reach for. It is not that one causes the other. It is that both are the same lesson, taught twice. Both are about the gap between how safe a place looks on an ordinary day and what it is actually capable of when the strain that has been quietly accumulating finally releases. The islands looked safe from great earthquakes, until the instruments showed the strain piling up beneath them. The world's coastlines looked safe from a certain ceiling of storm, until the ocean's heat began quietly lifting that ceiling. In both cases, the danger was building in silence, invisible to anyone who was not measuring, and in both cases the warning was there for anyone willing to look. Let me bring all of this together, because the real story of tonight is bigger than one storm, and it is the part worth carrying with you after the wind has passed. Part 14. The Gap Between Calm and Catastrophe. Step back from all of it for a moment, far enough to see the whole shape of what we have been looking at tonight, and a single pattern comes into focus, the one that I think actually matters. We started with a storm, a real, specific, dangerous storm, Mekkhala, climbing towards super typhoon strength over the warmest water on Earth and turning toward a chain of islands where more than 1 million people live. And we did something with that storm that is worth naming before we finish, because it is the whole method of how you actually understand an event like this rather than just react to it. We refused to stop at the headline. The headline is that the storm is strong and it is coming, and that is true, and for the people in the path it is the only part that matters this week. But for the rest of us, watching from a distance, the headline is where understanding begins, not where it ends. We asked where the storm came from, and the answer told us about the warm pool and the engine of these systems. We asked why it grew so fast, and the answer told us about ocean heat and the rising ceiling on what storms can become. We asked why 2 agencies disagreed about its strength, and the answer told us about measurement and the way honest discrepancies get mistaken for lies. We asked what was beneath the place it was aiming at, and the answer opened up an entire second story, older and slower than the storm, about a fault that has been loading in silence beneath a chain of islands that have been drowned before. That is the difference between watching a disaster and understanding one. Anyone can see the storm. Understanding it means following each question to the thing underneath it, and then following that thing to the thing underneath it, until the single event in front of you connects to the larger patterns that produced it. A storm becomes a lesson about a warming ocean. A fault becomes a lesson about the gap between how a place looks and what it can do. A disagreement about a category becomes a lesson about how misinformation breeds in the cracks between honest sources. None of these connections diminish the storm. They place it, they give it a context, and they turn a frightening night into something you can actually learn from rather than just be frightened by. And the connections we drew tonight were real ones, which matters more than I can say, because the temptation, always, is to draw false ones. The false connection, the storm will wake the fault, the storm was steered, the strength is being hidden, those are the easy stories, the ones that require no measurement and reward no patience. The real connections are harder won and less dramatic, and they are the only ones worth having, because they are the only ones that are true. So as we come to the end, hold on to the method as much as the facts. Ask what is underneath, follow it down, refuse the easy story and do the work of finding the real one. That is how you turn a storm into knowledge, and knowledge, in the end, is the only thing any of us can build against a world this powerful and this loaded. We traced its birth from an unremarkable cluster of thunderstorms, watched it feed on an ocean loaded with more stored heat than usual, watched it strengthen so fast that it earned the one-phrase forecasters fear, and watched the invisible hand of a pressure ridge steer it towards southern Japan. We sorted out why one screen says Category 4 and another says 5, and we looked clearly at the three weapons it brings: the wind, the surge, and the days of drowning rain. That alone is a serious, urgent story, and for the people in its path it is the only story that matters this week. But underneath it, we found a second story, older and slower and in some ways more unsettling. We found that the islands this storm is aiming at sit on top of a subduction zone that was long dismissed as quiet, a trench that the textbooks called weakly coupled and safe. And we found that this reputation was a kind of comfortable fiction, because the ground itself, measured millimetre by millimetre, has been quietly confessing that it is locked and loading, that a shallow patch of it may be capable of a magnitude in the 8s, and that 2.5 centuries ago it proved exactly what it could do when it drowned roughly 12,000 people on these same islands in a single morning. The danger was never gone, it was just silent, and silence is not the same as safety. And here is the thread that ties the storm and the fault together, the real one. Both are about the distance between how a place looks and what it can do. An island on a calm June morning looks like paradise, not like a place where the sea once stood up tens of meters tall. A patch of warm ocean looks like a holiday postcard, not like the fuel tank for a machine that can flatten a city. The strain in a locked fault accumulates in total silence, invisibly, year after year, until the instant it does not. The heat in an ocean accumulates the same way, quietly raising the ceiling on what is possible until a storm comes along and cashes it in. In both cases, the catastrophe is built in advance, in plain sight of anyone who is actually measuring, and invisible to everyone who is only looking. That is why I do not think the right feeling to take away from tonight is fear. Exactly. Fear is what the conspiracy theories sell, the manufactured storm, the storm that wakes the fault, the hidden hand. The truth is less lurid and far more useful. There is no hidden hand. There is only a world that is more loaded than it looks, in more places than we tend to admit, and a set of instruments and sciences that can, if we pay attention to them, show us the strain before it releases. The forecasters saw this storm coming days before it turned toward Japan. The geologists have been watching the ground beneath these islands flex for years. The warning in both cases was there. The only question is whether anyone listens to it in time. So as Mekkhala makes its final approach over the coming days, watch it. Watch the size of it, not just the category. Watch the turn. Watch the official word from the people whose job is to track it, and spare a thought for the more than 1 million people who will spend the next nights listening to the wind tearing at their homes and the sea pressing at their shores. But carry the larger lesson too, because it does not stay in the Western Pacific. The places we assume are safe only until something we were not measuring proves otherwise. The ground can be loading in silence. The ocean can be loading in silence. And the most dangerous words in the entire language of disasters are the ones people say about a place right up until the morning it happens. It has always been quiet here. I will leave you with the thought that has stayed with me as I have watched this storm climb and this fault sit silent beneath its target. We live, all of us, on a planet that is far more active and far less settled than the calm of an ordinary day suggests. The ground beneath our feet is moving, slowly, constantly, locking and bending and storing energy in places we're only beginning to be able to measure. The oceans around us are warming and shifting, raising the ceiling on what the sky can do. Most of the time, none of it touches us, and we go about our lives on the comfortable assumption that the world is as steady as it looks. Tonight is one of the times that assumption is being tested, over a chain of islands in the Western Pacific, and the people there are about to be reminded the hard way of something the rest of us are usually allowed to forget. The reminder is this: the world is not waiting to harm us, and it is not plotting against us, and there is no hidden hand behind the storm or the fault. But it is powerful beyond our scale, and it is loaded in more places than we like to admit, and it does not announce its worst days with anything more than the quiet, measurable signs we are finally learning to read. The only question that has ever mattered is whether we learn to read them in time. Tonight, it is not quiet, and the storm is still growing,